Okay, Assalamu alaikum and very good morning to everyone. Yesterday I gave you a brief introduction about gyroscope and we learned what is a gyroscope. Actually, it is a device for measuring or maintaining the orientation and it is based on the principle of conservation of angular momentum. Now, in order to understand it fully, let us watch this video again. Yesterday it was not clear.
Hello.
Hey everyone, it's me, Derek, from the channel Veritasium. And I've been following this series by Destin on Smarter every day about helicopters, and gyroscopic precision is just one of those things that still blows my mind as it did Destin's. So I'm here at the University of Sydney, my old stomping grounds. I'm going to borrow some of their lecture dem equipment to hopefully teach you a bit about how gyroscopic precision works.
The first thing I need to do is talk about vectors, because a lot of things in physics are vectors. That means they have direction. So an example would be momentum and force. Those are two examples of some pretty common vectors. So if I have a cart moving along here, it has some momentum in that direction, and if I apply a force to it, I can change its momentum. So for example, if I push it to the right, then its momentum will increase to the right. It all makes a lot of sense. Well, there's a similar statement we could make about rotating bodies, which is that a torque increases the angular momentum of an object in the direction of that torque. So let's try to figure out those terms. If I apply a force down on this side of the wheel, I create a torque. Now, torque is force times the distance from the rotating axis. You could call it R. So torque is the force applied times the radius away from.
This torque is in the plane of the screen. This torque is applied in the plane of the screen, that is in the plane of the wheel.
From the turning axis. Now what's the direction of that torque? Well, we actually use a right-hand rule to define this. And so what you do is you put your fingers in the direction of the radius from the turning axis and curl them in the direction of the force, and your thumb points in the direction of the torque. So the torque is actually out this way at 90 degrees to the force. The force is down that way, but the torque vector is actually pointing out this way.
This is the direction of the torque given by right-hand rule, right? So if you apply the right-hand rule, the direction of the torque will be perpendicular to your screen, outward. Okay. Now direction of torque, direction of angular velocity, direction of angular momentum. All these angular direction of all these angular quantities is given by right hand rule, right? So this way, how he is showing the direction of torque. Similarly, the direction of angular velocity, direction of angular acceleration, direction of angular momentum will also be shown by right hand rule. So you see the torque is in the plane of the screen and the direction is perpendicular to the plane of screen. You please remember.
So the angular momentum of this wheel is being increased in that direction. So the more I apply this torque, the more I increase the angular momentum of the wheel in the direction of the torque. So I'm making this wheel have a very large angular momentum out towards the camera, out towards you. Now before I go any further, let's have a look at this setup that I've got. I have a wheel here hanging from only one side by this rope. And so right now there's actually a torque on the whole system if I let go, because the weight of this wheel is pulling down, and that force is applied at this distance away from its pivoting point there. So if I let go, well, it does exactly what you'd expect.
You see the self weight of the wheel, it is producing a torque about supporting rope, right? And under the action of this torque, the wheel swings down.
So if I let go, well, it does exactly what you'd expect. The wheel swings down this way. But I want to see that as an example of rotational motion. There's a torque which is pointing out this way, which is trying to increase the angular momentum of the system in that direction. Now, angular momentum in that direction requires that the whole system starts swinging anti-clockwise. And so that is what happens. But what happens if I only let go after I've already spun up the bicycle wheel? Well, in that case, the bicycle wheel would already have angular momentum this way, and so a torque pushing that way actually swings this angular momentum around that way. Okay, so let me try to get the wheel spinning and make it work.
Now, when the wheel is rotating, you will see that it will not swing down. Rather, it will swing in a perpendicular plane. This is called gyroscopic precision. And this is happening because of the torque applied to the wheel by rotating it.
Come on. Oh, look at that. It's rotating as we predicted. See, the angular momentum vector is pointing out this way, but torque is pushing it this way. So angular momentum, torque, and torque is pushing that angular momentum vector around. Except not for long, because this appears to be a quite friction.
Okay, now you understood what is gyroscopic precision? When the wheel was not rotating, under the action of torque produced by its own weight, it swings down when it leaves it, when he leaves it. Okay, but when it makes the wheel to rotate and then leaves it, it does not swing down. Rather, it rotates in a vertical plane. This is because of the gyroscopic effect. I hope you understood gyroscopic effect. Please respond. Okay, was the video clear today? Okay, now we will see the mathematical analysis of this precisional angular motion. Are you able to see the paper view now?
Yes, sir.
Okay, I draw a simple diagram and explain you what is precisional angular motion. Okay. Now suppose we have a disc. We have a disc rotating about an axis OX in anti-clockwise direction. This is the direction of weaving. From this direction, you are weaving. I draw an eye here, indicating that this is the direction of weaving. Okay, this is rotating. When you weave from this direction along OX, the direction of rotation is anti-clockwise. It is rotating with angular velocity omega. Okay. Now let us assume that this spin axis, this axis, it is called spin axis, right? It is rotated by an angle delta theta. This spin axis is rotated by angle delta theta in time delta t, right? So that the new position of the axis is OX dash. So this becomes your new spin axis. Okay. Now angular velocity here, when the disk was rotating about spin axis OX was omega. Now suppose the new angular velocity when it is rotating about new spin axis is omega plus delta omega. Okay. So this is a simple representation that this disk is rotating about spin axis OX, right? And in time delta t, this spin axis rotates by an angle delta theta to take the new position OX dash. Now the angular velocity has changed from omega to omega plus delta omega. Okay. Now this disk is actually perpendicular to the plane of the figure. This disk is actually perpendicular to the plane of the figure, plane of the paper. Okay. Now I draw a vector diagram representing the direction of these angular velocities. Now while showing you the video, I told you the direction of torque or couple or angular momentum or angular velocity is given by right hand rule. So when you apply the right hand rule to this axis OX, the direction of this angular velocity will be this direction, okay, perpendicular to the plane of the disk. I name this vector as, suppose this is the vector, okay, I name this vector as OX. Okay. Now when the disk is rotating about new axis, new spin axis, its velocity will be given by this direction, applying right hand rule, right, to this axis. If I apply right hand rule to this axis, this will be the direction. Okay, this will be the direction of angular velocity, new angular velocity. So this vector is, I name this vector as OX dash, and magnitude of this vector is of course omega. Magnitude of this vector is omega plus delta omega. These are vector quantity, so I draw the vector here. Not drawn in the textbook, but I am drawing it here. Okay. Now what will happen? This vector x dash, this vector x dash will represent, this will represent change in angular velocity. Okay, change in angular velocity. This vector. Did you understand this vector diagram? This angle again is delta theta. What I am doing is I am representing angular velocities at initial position and at final position by vectors. So at initial position, this angular velocity will be directed along OX, right? And this is by right hand rule. Along the new axis, it will be directed along OX dash by right hand rule. The magnitude of angular velocity at new position is omega plus delta omega. Magnitude of angular velocity at initial position is omega, right? Now, by law of vector addition, this represents change in angular velocity, right? So this OX plus x dash will be equal to OX dash. This is the vector. This is the law of vector addition. Triangle law of vector addition. Is it clear?
Yes, sir.
Okay. Now what I'm doing, I'm drawing from x dash, I'm drawing a perpendicular here, 2-point R. Okay, 2-point R, right? Now you see, if I consider these two vectors, x dash, this vector, which is representing change in angular velocity, it will have two components, xr and rx dash. Okay, it will have two components, xr and rx dash. So component xr, right? This component xr, it represents change in velocity along OX. Component rx dash represents change in velocity perpendicular to OX. You understood this? Component xr represents change in velocity, change in angular velocity along OX. And component rx dash represents change in velocity perpendicular to OX. Okay. Now therefore, I find the expression for angular acceleration in the direction of OX and in the direction perpendicular to OX. So I assume let alpha t is angular acceleration in direction OX and alpha c angular acceleration perpendicular to OX. Right? So what is angular acceleration? Angular acceleration is nothing but rate of change of angular velocity. Are you familiar with this definition? Angular acceleration is rate of change of angular velocity. Is it clear?
Yes, sir.
Therefore, when I want to find alpha t, that is angular acceleration in the direction OX, so I will take change in velocity along OX. So change in velocity along OX is xr, right? Vector xr divided by time is delta t. So this is rate of change of angular velocity. Okay. Now xr is nothing but vector or minus ox on delta t. Vector xr is nothing but vector or minus ox. The remaining is xr. Okay. Now you see vector or. If you consider the triangle ORX dash, if you consider the triangle ORX dash, right? So this is vector OR is nothing but the cosine component of vector OX dash, right? So I can write this as OX dash cos delta theta, because vector OR dash is cosine component of OX dash minus OX dash on delta t. So we got expression for alpha t as OX dash. Now what is OX dash is omega. Omega cos delta theta minus OX is OX. This is not OX dash, this is OX. OX is again omega divided by delta t. Okay. Sorry, OX dash is omega plus delta omega. This is omega plus delta omega. Okay. So this expression becomes omega cos delta theta plus delta omega cos delta theta minus omega on delta t. Okay, I multiplied cos delta theta to this bracket. Okay. Now, as delta theta is very small, so I can take cos delta theta equal to 1 because delta theta is very small. Say smallest value of delta theta can be 0. Cos 0 is 1. For smaller values of delta theta, cosine of delta theta will almost be equal to 1. Right? When you put cos delta theta equal to 1, you get this expression alpha t will be equal to omega plus delta omega minus omega upon delta t. So omega omega cancel. What you get is alpha t equal to delta omega upon delta t. Now this is in terms of partial derivative, right? So this represents instantaneous value of alpha t. Instantaneous value of angular acceleration in the direction of OX. To find the total angular acceleration, what we do, we take limit delta t tends to 0, delta omega by delta t, and this is equal to total derivative of angular velocity with respect to time. Okay, now this is the expression for angular acceleration along OX. Let me explain you again. You see, angular velocity is changing, and this vector is representing change in angular velocity. Now, as angular velocity is changing, this disk is acted upon by angular acceleration. This angular acceleration will have two components. One component along OX, the other component perpendicular to OX. Now, in order to find component along OX, we use this expression alpha t equal to change in angular velocity along OX divided by time. Okay, from this we find angular acceleration in the direction of OX. Now we have to find expression for alpha c. Alpha c is angular acceleration perpendicular to OX. Now angular acceleration is again change in velocity divided by time. Now from this diagram, tell me which vector is representing change in velocity perpendicular to OX. Please let me know which vector is
Rx bar, sir.
Which vector is representing change in velocity perpendicular to OX. Yes, it was correct answer. Tell me again.
Rx bar, sir.
Rx dot, correct. Rx dot, this is representing change in velocity perpendicular to OX. So in order to write the expression for, in order to find the expression for alpha c, I will consider vector Rx dot upon delta t, right? Now you see the vector Rx dot, if you consider the triangle ORX dot, it is nothing but the sine component of vector OX dash. OR was cosine component. Rx that is sine component of vector OX dash. So I write this as OX dash sine delta theta on delta t. Now OX dash is nothing but omega plus delta omega. Its magnitude is omega plus delta omega. Sine delta theta upon delta t. Okay. Now I again multiply this sine delta theta to this bracket, right? So this will become alpha c will be equal to omega sine delta theta plus delta omega delta theta sorry, this is omega into sine delta theta plus delta omega into, I write this again, alpha c equal to omega sine delta theta plus delta omega sine delta theta about delta t. Okay. You please write till here, then I will continue. I will give you time to write. Okay, now alpha c, right? Since delta theta is small, I can write sine delta theta. This will not be equal to 1. Rather, it will be equal to delta theta. Okay. So this expression will become alpha c will be equal to omega delta theta plus delta omega delta theta upon delta t, right? Now see, delta omega delta theta both are very small quantity, so their multiple will also be very small. Therefore, we can neglect product of delta omega delta theta. Okay, we can neglect. So this expression for alpha c will become omega delta theta by delta t. You understood why did we neglect? These are small quantities, so their multiple will be further very small. Okay, that's why we neglect this. Okay, alpha c, we got expression omega delta theta by delta t. This is instantaneous value. To find the total value, we take the limit delta t tends to 0 omega delta theta upon delta t. Omega is constant, so we can write it outside the limit. Delta theta by delta t, and this is nothing but omega d theta by dt. Okay. Now I again move back to this diagram. D theta by dt, what does it represent? See, delta theta is angular displacement, delta t is time. So delta theta upon delta t is nothing but angular velocity. But this is not the angular velocity of disk. Angular velocity of disk is omega. Delta theta upon delta t, this is the angular velocity of spin axis, the angular velocity with which the spin axis rotates. Do you understand? Because delta theta is the angular displacement of spin axis. So delta theta upon delta t is the angular velocity of spin axis, the angular velocity with which the spin axis rotates. Now this is the spin axis, right? It is rotating this way. So the velocity with which the spin axis rotates is given by delta theta by delta t, rate of change of angular displacement. So this term, okay, delta theta by delta t actually represent velocity with which spin axis rotates, and this is called omega p. So alpha c is called is equal to omega into omega p. This is the formula, okay, of acceleration, angular acceleration perpendicular to OX. Okay, omega is called velocity of precision. Okay, omega p is called velocity of precision. Okay, so you understood what is velocity of precision? Actually, velocity of precision is what? It is the velocity, angular velocity by which the spin axis rotates. This angular velocity is velocity of precision. Now this spin axis, of course, it is rotating about an axis perpendicular to plane. Okay, this axis is called axis of precision. This axis is called axis of precision. The axis about which the spin axis rotates is called axis of precision. ये जो perpendicular axis है, ये जो मैंने पेन लगाया है, this is the axis of precision. You understood? Now this component of acceleration perpendicular to OX, alpha c. Okay, this is called gyroscopic acceleration. Gyroscopic acceleration, alpha c, whose formula is omega into omega p. The total acceleration of the disk alpha will be equal to alpha t plus alpha c. Alpha t was d omega by dt. Alpha c is omega into omega p. Right? Now I explain you the concept. You remember there are two components, d omega by dt and omega into omega p. The vector sum of these two is total acceleration of disk. So what happens when this spin axis rotates? This spin axis rotates by an angle delta theta. This is called precisional angular motion, right? Then this disk is acted upon by two acceleration. One acceleration is along OX. We call it alpha t, which is equal to d omega by dt. The other acceleration is perpendicular to OX, right? And this acceleration is gyroscopic acceleration, right? Now you see, linear acceleration is produced by force, and angular acceleration is produced by torque or couple, right? A force produces linear acceleration and a torque or couple produces angular acceleration. Now if there is a angular acceleration, gyroscopic acceleration in this direction acting on the disk, that means there is a couple acting on this disk, right, in this direction. This couple is called gyroscopic couple. This couple which produces this gyroscopic acceleration alpha c is called gyroscopic couple. You understood this? So what happens when a rotating disk, its spin axis rotates by some angle, it is acted upon by two acceleration, two component of acceleration. One is along OX, other is perpendicular to OX. We are interested in a component perpendicular to OX, which is gyroscopic acceleration. Now this gyroscopic acceleration must have been produced by some torque or couple. So the torque or couple which produces this gyroscopic acceleration perpendicular to OX is called gyroscopic couple. Is it clear? Okay. Now you remember the video